All right, welcome back. And it's my great pleasure to introduce Winnie. She gave us the opportunity to start a conference series 10 years ago. So we're glad to have her back as a plenary speaker. So she will talk about hypergeometric functions, Galois representations, and modular forms.
Thank you. Thank you for the introduction. It's a great pleasure to return to LSU to visit. It's a wonderful conference. We'd like to thank all the organizers for the invitation. So today I will talk about the relations between hypergeometric functions, Galois representations, and modular forms. So in particular, I will report on joint work with 3 sets of co-authors. The first set with Tong Liu and Lin Long on the modularity of low-dimensional hypergeometric Galois representations. The second set is Lin Long and Fantin Tu on the interpreting WIPO 756 identity via Galois representations and modularity. The third paper is with Bill Hoffman, Lin Long, and Fantin Tu on the traces of Hecke operators via hypergeometric capital sums. As you can see, that all but one co-authors are here. So, so the experts are in the audience. So I'm only responsible for all the mistakes. And we have heard from many people's talk mentioning the various subjects of that I'm going to talk about. So the first part of the talk will be a review, especially for the experts. So the hypergeometric function was initially introduced by Euler, and the Gauss was the first person who systematically studied hypergeometric functions. So at that time, the hypergeometric functions are what we call the 2F1, which involves, 3 complex constant parameters, A, B, and C. It's defined using the poke hammer symbol. So here's like A parenthesis R is A times A plus 1 times A plus R minus 1. In particular, say 1 parenthesis R would be R factorial. Okay. And this poke hammer symbol, A parenthesis R, is gamma of A plus R over gamma A. Okay. And this series, well, is defined when the infinite series converges. Okay. And the Riemann was the first one who systematically studied the 2F1 hypergeometric functions in terms of differential equations. So notice that 2F1 satisfies a second-order linear differential equation. Okay. You can see that this the parameters A, B, C show up in the equation. Sorry. And this equation has a regular singular points at 0, 1, and infinity. Okay. And that the original function 2F1 ABC is a solution at z equal to 0. And then there are lots of relations among the hypergeometric functions. And I will talk about connections between hypergeometric functions and modular forms. This part is less well known. Okay. And normally when we teach or we learn modular forms in school, usually they don't talk much about connections with the hypergeometric functions. Okay. So as we are all familiar with, the group SL2R acts on the upper plane by fractional linear transformations. So let's take a discrete subgroup of SL2R, so even a congruent subgroup if you wish. Okay. And so we only consider those such that when you look at the orbit space, so that's the upper plane modulo the gamma, and you compactify by add the cusps if needed. Okay, such that it is a genus 0 projective curve. Okay. So because it has a genus 0, so it has a parameter or can be parameterized by a meromorphic function into the, well, which has a simple pole. Okay, we call it lambda gamma. Okay. So normally we use the variable, use tau for the variable on the modular curve, and use z as a variable on the P1C. So the z is a lambda tau. Okay. So our modular form is defined on the upper plane as a holomorphic function. So okay, say it has weight k, and it doesn't satisfy good differential equation in the variable of tau. But if you view that as a variable in z, then it satisfies a linear ODE of degree k plus 1, okay, and with nice algebraic coefficients. Okay. And when the weight k is equal to 1, so sometimes we can recover a modular form from the 2f1 function. Namely, if you replace that z by lambda of tau, then you get a function on the upper half plane, and that function is a weight 1 form. Okay. And if the modular curve has genus greater than 0, then we cannot do this globally, but we can still do this parameter locally. So for instance, if we take the group to be SL2R, so normally we take a parameter to be the J function, but here let's take a 1728 divided by J. Okay, that's also a parameter. Okay. And we know that SL2Z doesn't have modular form of weight 1, and the lowest weight has weight 4. That's Eisenstein series E4. And indeed, that is 2F1 evaluated on using this lambda raised to the 4th power. So that gives us modular form. And another example is a group is gamma 1, 4. And we choose the parameter using the theta functions, theta 2 and the theta 3, theta 2 over theta 3 to the 4th. Then in this case, you just use lambda by itself. Then we recover theta 3 squared, which is a modular form of weight 1 for this group. And the third example is what we call the triangle group. So a triangle group has we usually use notation E1, E2, E3 to denote it. So that means that this group has 2 generators. So first generator has order E1, second generator has order E2, the product has order E3. So that's the only relations among them. And so it is a arithmetic triangle group. And Ivan Yana has gave a nice basis for the space of the weight k modular forms for this group using a parameter lambda and also a 2f1 function where the parameters A, B, C are expressed using the order E1, E2, and E3. So now, knowing the 2f1 function from there, we can very easily generalize it to the nfn-1 function, where we just use the n Pochhammer notation on the numerator and also n Pochhammer notation on the denominator, except that the first one, B1, we always choose it to be 1. So normally we just have B2 up to Bn. So that's where this n-1 comes from. So, and we will collect this, the first row, the A's, we call that lambda, alpha, and the B's with B1 equal to 1, call that beta, and put it together. This is what we call a hypergeometric datum. Okay. So each, and this n is called the length of the datum. Okay. So just like what we have seen for the 2f1 function, for the nfn-1 function, it satisfies an nth order linear ODE with the 3 regular singular points at 0, 1, infinity. Okay. So now let's look at the P1C and remove these 3 points, 0, 1, infinity. So at any non-singular point, And so this nth order linear differential equation would have the solutions through this given point, and that will give you an n-dimensional vector space. So each point, you collect all the solutions through that point, and as you vary the points among all the non-singular points and collect them, you get a sheaf or what they call a local system. Okay. So now, if you start with a non-singular point, and if you have a loop, well, on this P1C with 3 points removed, so you start with this point, then you move around along this cycle that you have chosen analytically. So when at the end, when you return to your starting point, usually you will end up with another solution through the same point. So starting from that solution, well, along this cycle, get another solution. You can view this as a representation of this cycle, moving from one solution to the other solution. So this is called the monodromy representation of the fundamental group. So this is the story on the complex side, this analytic story. Okay. Now, we are also interested in the other side, the algebraic side. So to have algebraic side, now we are going to restrict our to be non-zero rational numbers. Okay. And we will call our hypergeometric datum primitive if the difference between AI and the BJ are not integers. Okay, so this we will always assume. Okay. And we look at the denominators in AI and the BJ and look at the least common denominator. We're going to call that level of this datum, that's M. Okay. So now on the algebraic side, we are going to have a very similar situation than what we have just seen over the complex side. Okay. So let's take any prime L. So Katz now has introduced a rank N hypergeometric sheaf, okay, on GM. So the GM means it's a multiplicity group. So GM at any field is the multiplicity group of that field. So you can think of this GM as a projective line with 2 points removed. Okay. So it just has one more point, 1 there. So then, so first we have this sheaf on GM, but also, and we also have explicit action of the Galois group from Q bar over the cyclotomic field joining M through the 1. So this I'm going to denote by G of M. Okay. So if we take a point which lies in the cyclotomic field joining M through the 1, which is non-zero, so then well, through that point we have a degree N. Well, that l-adic vector space, then the Galois group is going to act on that l-adic vector space. And to describe this Galois action, well, we describe it by giving the traces of the Frobenius elements. And these traces happens to be the hypergeometric character sums. Okay? And they are finite field analog of the hypergeometric functions that we have just defined. Okay? So these hypergeometric character sums were studied by Katz to begin with. And Fuselier, Long, Ramakrishna, Swisher, and Tu recently published a very, very nice MS memoir, which studied this hypergeometric character sums extensively. So that's a great reference, which I recommend to everyone. So I should go back. So there's also some differences between the algebraic side and the complex side. So on the algebraic side, these Galois representations only depends on the parameters modular the integers, okay? And also, when you will look at the hypergeometric function over the complex numbers, it doesn't matter the orders of A's and the B's. When we go to the algebraic side, when we permute orders of A and the B's, we would end up with the characters we would end up with Galois representations differ by a one-dimensional twist. Okay. But on the other hand, if we permute the columns around, then they will stay the same. Okay. So we were going to say that this hypergeometric datum is defined over Q. If these columns are modulo Z, when we multiply by the integers co-prime to M, we'll just permute these column vectors. Okay. When that happens, we will say that a datum is defined over Q. Okay. When the datum is defined over Q, then the Katz representation originally for the representation of Galois group from Q bar to the cyclotomic fields now can be extended further down to the full absolute Galois group of Q. Okay. And one such extension was studied by Boykers, Cohen, and Melit, which we call that a BCM representation. Okay. And BCM representation, when you look at the Frobenius traces, they are also explicitly given by character sums, and it's called the HP function. Okay. For instance, if we look at the prime P count to 1 modulo M, then if you look at this HP function as such kind of prime P, then it's explicitly determined using the Gauss sums. Okay. So earlier, when we defined the hypergeometric functions, we use the Pochhammer notation. We say that a Pochhammer notation is the quotient of two gamma functions. And the finite field analog of gamma function is exactly the Gauss sums. And you will also see this A plus R and A here. So the Gauss sum certainly, well, we will have a multiplicity character and additive character. So it's going to be independent choice of additive character. So for the multiplicity character, we use the fact that all the characters for the multiplicity group of FP is cyclic, so we just choose a generator. We express all the other characters as a power of this character. Then you can see here, the first notation here, it's you see AJ, here's K, so you can think of this like a gamma of AJ plus K, and here divided gamma of AJ, okay. And then the B's should go in the denominator, then we use the Gauss sum property, then we express that in terms of the inverse of omega, so we put it down in a similar way. And so the product J from 1 to N, that accounts for A1 up to AN, the length N. And finally, originally the summation was from R from 0 to infinity, but now we only have P minus 1 characters, so we sum from 1 up to P minus 1. So we use each character, we evaluate at this element lambda. So you can see that this HP function is really finite field analog of the hypergeometric function. Okay. So I said that, so when the datum is primitive of length N and defined over Q and with the level M, then we will have this BCM representation almost, yeah, I can write down it for Frobenius, really expressed in terms of this HP function. And the slight difference is that if we look at the representation of fiber at lambda here, then here the HP is at 1 over lambda. Then in front of it, there's some small modification. There's a power of P, which is related to the number of the integers inside the beta. So it will be P raised to some integral power. Okay. And also there's a sign in front of it. Most of the time, this sign is equal to 1. And the only exception is that when the AIs in the alpha is counted to 1/2 modular integer, and 2 exactly divides the level M. Okay. Otherwise, the sign is not there. But the upshot is that BCM representation of the Frobenius elements in Z, so they are integral. Okay. And so in general, a BCM representation on each fiber will have its degree that's equal to the dimension of the space n if this parameter lambda is not equal to 1. When lambda is equal to 1, it degenerates. So the dimension goes down by 1, equal to n minus 1. Okay. Another property we will use is that when n is an odd integer, then the image of this Galois representation is orthogonal type. And if n is even integer, then image is symplectic type. So let me give you an example. It turns out that this example already shows up in quite a few talks in this conference already. So I would take the easiest one. We'll take alpha equal to half, beta equals 1, 1. So then this datum is definitely is primitive and defined over Q, and the level is equal to 2. Okay. So in this case, the CATS representation agrees with the BCM representation. They are both for the Galois group over Q. Okay. And if we look at the hypergeometric character sum at lambda, actually it's very explicit. It's just a bunch of plus minus 1 or 0. Okay. So it is summing over the elements in the finite field Fp of a quadratic character evaluated at x times 1 minus x times 1 minus lambda x, okay, with a minus sign in front. So when we go back, look at a BCM representation, in this case, it's a trace that Frobenius P is exactly equal to this hypergeometric HP function at 1 over lambda. Okay. So when we see this lambda, when this HP function here, I mean, we have product of 3 factors of x. So, and with quadratic factor outside, immediately we would think about the elliptic curve defined by y squared equals x times x minus 1 times x over lambda minus 1. I have x over lambda here because it's at 1 over lambda. Okay. So, we see that when lambda is not equal to 1, the numbers we have here is exactly what we call the AP associated to this elliptic curve from point counting. So this tells us that this BCM representation is a 2-dimensional because it has for length is a 2, lambda not equal to 1. And this Galois representation we know very well. It is the usual Galois action on the L-adic Tate module of this elliptic curve. Okay, and by the Taniyama-Shimura conjecture, we know that this Galois representation is modular. When lambda is equal to 1, when you go back and look at this character sum, it is equal to 1. This tells us that this BCM representation at lambda equal to 1 is the trivial representation. So degree goes down by 1. Okay. So now we are interested in the case where the datum using the AIBJ, which are non-zero rational numbers. Okay. And so we have seen on the complex side, we have representation of fundamental group. And on the other side, we have representation of Galois group. So how are they related to each other? Okay. So first, let's look at where they are defined. So for the fundamental groups, defined on the P1 minus 3 points. On the Galois group, it's defined by 1 more point. So let's forget about 1. So we also remove 3 points. Then all the Galois representation will all have degree n. Okay. So it turns out that they are related by the état fundamental group of the generic fiber. Okay. So the Galois group, which shows up in the CATS model, CATS representation there, is a quotient of this état fundamental group. And the kernel is given by the profinite completion of the fundamental group we are interested in. So this is how they are related. Okay. So what we are going to do is that we are going to exploit this relationship between complex side and algebraic side, or analytic side and algebraic side. And also because this CAS representation and the BCM representations, they all arise from geometric construction, and they ramified at only finite many places. According to Langland's philosophy, they should be automorphic. And I think this morning, John Voigt will explain, being automorphic means its L function agrees with L function of some automorphic form. Okay, so we are going to study that. So for me, the very basic or the first relation we exploit is the so-called Clausen formula. And this Clausen formula plays a very important role in all the works that I'm going to report. Okay. So on the complex side, the classical Clausen formula tells us that I have product two 2f1 functions, and they will give us a 3f2 function, and together with some a function in front. Okay. And the finite field analog of Clausen formula was given by Evans and Green. Okay, so it's similar. It's also product of two HP function, or I do the SQ function. HQ function, well, Q is a prime power. Okay, and you see the others. Well, on the left side, each HQ function will using the datum of length 2. And the other side is HQ function with datum of length 3, okay? And in front of that, it has a quadratic character, which corresponds to this 1 minus z. There we have minus t, 1 minus t, but it does have one extra term. This extra term is either q or 1 there. Okay. So we have this identity when this parameter t is coming from the finite field. It's not 0 and not equal to 1. So I will come back to explain the meaning of this. And when t is equal to 1, this analog takes a different form. Okay. So basically, so well, it depends on this omega that we choose. So if omega, well, raised to this q minus 1 times a plus b is a square, then you see this HQ is expressed using the Jacobi sums. Okay. And when it's not a square, it's equal to 0. Okay. So now let's go back. So these are the identities of the character sums. Now let's try to understand these identities from the viewpoint of Galois representations. So we should think of this HQ as a HP. So we have well, degree 2 Galois representation, and which trace of Frobenius P is equal to each character sum there. Okay, and when look at the choice of the parameter, actually it's written in such a way that the second Galois representation is the control gradient of the first Galois representation. And for the degree 2 Galois representations, the control gradient is equal to the original representation twisted by this determinant to the -1. So in other words, the left-hand side here, in terms of Galois representation, is the Frobenius trace of the degree 2 Galois representation tensor with itself up to a one-dimensional twist. And the right-hand side here, we have a degree 3 Galois representation with also a quadratic twist in front, plus a degree 1 Galois representation. So this, what means really is that we have a degree 2 Galois representation tensor with itself decomposes as its symmetric square plus alternating square. So degree 3 plus degree 1. This is how we interpret this identity when t is not 0 or 1. Okay. So when t is equal to 1, situation is different. In this case, the representation will generate. So when this length 3 at lambda equal to 1 will be a degree 2 Galois representation. So again, this represents the Frobenius trace. So this says that at half of the, so you should think of this P as variant. At half of the primes, well, when this omega to this exponent is a square, you can see that it's a sum of two characters. And these two characters also, they are, well, related. And they are conjugate in a sense, okay? And in another half of plane is equal to 0. So this tells you that this degree 2 representations actually is induced. It's induced from a character of a quadratic extension. So that's the way one reads the character sum identity. So with that explanation, now we can see to answer some questions, okay? So now if I choose my alpha has length 3, has a shape half 1 over d1, 1 minus 1 over d1. Beta has the same kind of shape with a different d's, okay? All beta is all 3 ones, okay? Now when d is either 2 or 3 or 4 or 6, then this datum will be primitive and defined over Q, okay? So we can talk about a BCM representation. So if we have lambda equal to 1, then this representation has a 2-dimensional, and we show that this is joint work with Tong Liu and Lin Long. We show that this one is modular and also has a complex multiplication. Okay. Then if lambda is not equal to 1, then this is a 3-dimensional. And this 3-dimensional up to the twist by character, it is the symmetric square of a degree 2 modular representation of GQ so that it is automorphic. So it's automorphic for G of 3. Okay. So next we want to look at a BCM representation which has degree 4, but has orthogonal type, okay? So to guarantee that it has orthogonal type, we're going to take data which has length 5, okay? And we look at the point lambda equal to 1. So that we know for sure the image is as a GO4 shape, okay? So then Tong Liu and JKU, they have shown that, so in this case, so there is a field which is either Q or quadratic extension of Q. When we restrict rho to that Galois group, it decomposes as a tensor of 2 degree 2 representations. So then with Tong Liu and Lin Long, we show that if this representation is induced from a character of a degree 4 extension, or if this field F is equal to Q, then we know for sure that this representation rho is automorphic. Yeah. If this field is real quadratic, then we know that this is a potentially automorphic. So for example, so this is one example where the alphas are all the halves, 5 of them, betas are all ones, that 1 here. So left-hand side is a trace of Frobenius P at the degree 4 representation of GO4 type, okay. Then we see that it's a product of 2 terms. The first term has a length 2, half, 1, 1 is the one we just looked at, and that lambda equal to -1. So this is a trace of degree 2 Galois representation. And the other factor here, well, has length 4, alpha and beta, and so it is defined over Q primitive, but at lambda equal to 1. So it's a degree 3 Galois representation. And so there's one property of that I didn't say is that this degree 3 Galois representation decomposed as a degree 2 plus degree 1, and that degree 1 will have a Frobenius trace equal to P. So when we remove that part, the remaining part has degree 2. So it's a product of Frobenius trace of 2 degree 2 representations. That means that it's a trace of the tensor of 2 degree 2 Galois representations. And one can check, verify that each is modular and with explicit modular form, well, identified. And the left-hand side is BCM representation and with a quadratic twist. How much time do I have? Okay, So then I come to the second piece that I'll talk about is a WIPO 756 formula. So this was originally proved by WIPO, which relates a 756 for hypergeometric function value at lambda equal to 1 with a shorter one for F3 with also value lambda equal to 1. And well, the difference is all by explicitly given by the value of the gamma functions. So this was proved using analytic means, and this identity holds when they say that both sides terminate, which means that one of the A, E, F, G should be 0 or negative integer, so that this hypergeometric function actually is a polynomial. Okay. So this is identity on the complex side. We want to see whether there's some corresponding interpretation on the algebraic side. Okay. So to get algebraic side, we're going to put some restriction on the parameter. We assume that we choose A to be 1/2, and we assume that the datum is so-called self-dual. So if I have a C, I will have 1 minus C. If I have F, I will have 1 minus F. So again, evaluate the lambda equal to 1. Okay, so we simplify this relation. Okay, and from the datum over there, that means that when we look at the Galois representations, we associate a datum to the left-hand side. The first one will have the datum alpha and the beta, which have length 6. 1/2 C, 1 minus C, 1/2 F, 1 minus F. And the beta will be automatically determined because the corresponding beta I plus alpha I is equal to 3/2. Okay. And similarly, so the second one will have length 4, will be 1/2 F, 1 minus F. And again, the beta will be such that the corresponding term will add up to 3/2. Okay. So we work on these two sets of the data and look at the, so in this case, it's very general. So we look at the CATS representation and find out their relations. So we show that when the two data are primitive, then, well, we come up with integer which is multiple of the level of both datum. So both data, so actually they are, this n is equal to m or twice of m. It's very close. Okay. So we compare the CATS representation associated to the first datum and the CATS representation associated to the second datum. Okay. Then we found that when we compute the trace, then the Frobenius trace of the left-hand side is equal to Frobenius trace of the right-hand side associated to the second datum, well, together with the twist by cyclotomic character. And then there's another piece is a degree 2 representation. So this is the representation of Galois group of level n. Okay. And when the first datum itself is defined over Q, then we know for sure that the representation on the left-hand side, well, is semi-simple. So we really have this isomorphism decomposed representation. So this is some relationship on the Galois representation motivated by the identity on the complex side. But I would like to point out that as I said, originally the WIPO identity assumes that the both sides terminate, namely one of the A, E, F, G is 0 or negative integer. But in our choice of this C and F thing, nobody is 0 or negative integer. So we have now some identity on the algebraic side. To me, it's an open question to see what is the corresponding relationship on the complex side. So then we can go further on the datum that data H1 and H2 that we have chosen. We notice that if the C and the F is one of the following 7 pairs, then the H1 will be also defined over Q. Okay, it's primitive and also defined over Q. And the H2 is primitive, but it's defined over Q only for the first 5 pairs. And well, for the last 2 pairs, it's not defined over Q, but still we can show that that Galois representation can be extended to GQ representation. So we just call that a BCM representation. Okay. And in this case, the level for both are the same. So they are representations of the same Galois group. Okay. So then we want to answer the question. So now we have representation of a Galois group over Q. We want to understand whether they are automorphic or not. Okay. So for the first one, for the second datum, it has length 4, lambda is equal to 1, so representation is 3-dimensional. In this case, decomposed as a 2-dimensional plus 1-dimensional representation. And the first datum has length 6, and lambda equal to 1, representation is 5-dimensional, decomposed as a 4-dimensional plus 1-dimensional. So we want to, the 1-dimensional is automatically automorphic. We want to know how about this 2-dimensional and the 4-dimensional ones, whether they are automorphic. Okay. So I'll start with the easier ones, the 2-dimensional ones. Okay. So the second datum, so we can prove that it is indeed automorphic, and we can identify the corresponding modular forms. Okay. So that means that we have this weight 4, say for instance, for the first pair, we have this weight 4, level 8 modular form. If you look at the AP, it's equal to the Frobenius trace at the P. So, and likewise with all the other pairs. Okay. So we also notice that this in the first case, the representation itself, the BCM is the same as the what's that called, the CAS representation. So it's not by extension, but for the other cases, it's really, the original CAS representation was defined over some cyclotomic field, which is not Q. So we actually extended to Q. So we could have chosen, well, a different extension. So we found some kind of pairs that differ by, in this case, they all differ by a character, but okay. So then for the first datum is the primitive part has degree 4. Okay. So let's recall the theorem here. Okay. So the degree 5 here is isomorphic to a degree 3 plus degree 2, and degree 3 here decomposes as a degree 2 plus degree 1. So the degree 4 representation here is a degree 2 plus degree 2, so it has 2 pieces. Okay. And the piece which has something to do with the second datum automatically has a cyclotomic twist in front of it. So we have this degree 5 BCM representation associated to the first hypergeometric datum. So it's degree 2 plus degree 2 plus degree 1. So the first part here comes from the sigma, the degree 2 one. So generically, as a weight 6 form with the different levels. When the weight drops, then we have the cyclotomic character in front to pick up the absolute value of Frobenius eigenvalue. Okay. Then the remaining part comes from the epsilon L times BCM representation associated to the second datum. Okay. So as I pointed out, for the non-uniqueness of the extension, so here the BCM representation itself actually picks up a slightly different. Instead of picking up the first one, it picks up the second characters, modular forms there. But anyhow, it's automorphic. Okay. Now I come to the last topic, okay, which is related to the trace of Hecker operators, I think which showed up in Bober's talk yesterday. Okay. So what we are interested in doing is to find an explicit formula for the trace of Hecker operators, TP, acting on the weight k+2 cos forms for the congruence group gamma. Okay. Now, if this gamma doesn't have any cusp, that means that we are looking at a group, which is on Shimura curves, then it just represents the modular forms. Okay. So this gamma is a congruent subgroup for SL2R. As I said that, so that the corresponding curves, either elliptic modular curve or Shimura curve. Okay. So here we assume that this X gamma is defined over Q. And if the group contains minus identity, then we only consider the even weight forms. Okay. So this question was previously done by various authors, say Oglen for gamma naught 4, Oglen Ono for gamma naught 8, Fréchet, Ono, Papanikolaou for new forms on gamma naught 8, and Fuselier for SL2D, and Lennon for gamma naught 3 and gamma naught 9. So they all use the Selberg trace formula, I think, which also shows up in Bober's talk yesterday. Okay. So what we would like to do is to express this trace of Hecker operator in terms of the hypergeometric character sums. There's a different expression. Okay. So without using the Selberg trace formula. So our idea is to use the geometric approach. Okay. So this will go back to the work for Deligne when he considered elliptic modular forms of integer weight k, and he constructed this automorphic sheaf for each weight k, weight equal to 1. So if the group gamma is torsion-free, then he uses the universal elliptic curves, okay, to construct that sheaf. And if this gamma is coming from the Shimura curve, then Shimura has did a similar thing using the universal abelian surfaces with a quaternion multiplication. Okay. But if gamma has torsion, then we choose a subgroup without torsion. We have the sheaf, then we do push forward. Okay. So here is the result. So that we can express the trace of Hecker operator on the space of cos forms of weight k+2 in terms of a Frobenius, trace of Frobenius of the P acting on the first cohomology group of the curve with coefficient in this automorphic sheaf. Okay. Then, so on the geometric side, we can apply the Lefschetz fixed formula. So we can express this trace of Hecker operator with minus sign equal to the sum of the Frobenius trace on the this automorphic sheaf at the points which are the modular curve over finite field FP. So what this really means is that we can reduce the computation of the trace of Hecker operator on the space of cos forms by looking at, so for each FP rational point on the curve, we just look at a point on the original curve, which project to this lambda here. I look at the fiber at that point. So there we have action of a Galois group. We look at the Frobenius P on that fiber. So that is, take a trace. So that is that number. So we reduce this computation of Hecker operator to the computation of Frobenius trace. So we convert the problems there. So now, well, for what kind of sheaf do we have explicit Frobenius trace? Hypergeometric sheaf we just talked about. So the idea is that to replace this automorphic sheaf by hypergeometric sheaf. Okay. So in the computation of this operator Hecke or TP of on different weight, the key point is really what happens on the two sheaves. If the group gamma doesn't have elliptic point, then the basic sheaf is V1, and all the rest basically is the symmetric power. If the group gamma has minus identity, then the base sheaf is V2, and the rest is symmetric power. Okay, but that's the idea. So as I said, so then we would like to replace this automorphic sheaf by something we know. We know the trace of Frobenius, so by the hypergeometric sheaf. So of course we have to choose this alpha and the beta cleverly so that this would work. Okay. So now suppose we have our choice of alpha beta. How do we know that our choice of this sheaf, well, how do they compare to V1 or V2? Okay. So here, again, we go back to this picture I said. So we first use a Katz rigidity theorem, which tells us that we first compare the complex side of the sheaves we have in mind with the automorphic sheaf. Okay. So I compare them. So in our case, our hypergeometric sheaf will differ from the automorphic sheaf on the complex side by a character. So we pick up that character. Okay. So we fix what happens on the complex side. Now we look at the algebraic side. So on the algebraic side, we compare, so with this new twist added to our hypergeometric sheaf, we compare that with the algebraic side of V1 or V2. Then the comparison theorem says that they differ by a character of finite order at any fiber at good point. Okay, so you just have to determine, choose a convenient fiber, and you can determine that character twist. Once you determine that, then we are done. Okay. But the idea to use hypergeometric sheaf comes with its natural constraint. Okay. So first, hypergeometric sheaf, as we said, is defined over projected line minus 3 points. So which means that your modular curve should have genus 0, should be defined over Q, and the 3 exceptional points should be Q rational. So those are the constraints. Okay. So that means that our group should have only 3 singularities. Okay, so that means that we look at the arithmetic triangle group. So then we identify that there are exactly 7 such kind of arithmetic triangle group that fits into the necessary condition. Okay, so the first 5 are actually the first 2 of them do have a model which do not contain minus identity. So it's gamma 1, 4 and the gamma 1, 3. Okay, and the remaining ones, well, they are projective group. So we leave that inside into SO2R. So that they, therefore, as such, they contain minus identity. So they are gamma naught 2, SO2Z, and gamma naught 2 together with the Atkin-Lehner involution at 2, and gamma naught 3 together with Atkin-Lehner revolution at 3, and another group 2, 4, 6. Okay. So let me say a few words about this last group, because all the other 6 groups here, they are familiar elliptic modular group. So the last group is live on the Shimura curve. Okay. So it comes from the quaternion algebra, indefinite quaternion algebra over Q, okay, which is discriminant 6. So you can choose a generator I squared equals minus 1, J squared equal to 3, and IJ equals minus JI. Then we look at, we choose a maximal order and look at the elements there with norm 1. So they play the role similar to SO2Z. Okay. And our group 246 is this norm 1 group, OB1, together with all the Atkin-Lehner involutions. Okay. And so I put all the corresponding of alpha and the beta. And you notice that the first alpha and beta is exactly the example that I gave at the very beginning. Okay. So here's our result. Okay. With the Hoffman, long and the 2. Okay. So let me first start with the last 5, which means the group contains the minus identity. So that means we only look at the modular forms with even weight. Okay. In this case, the Frobenius trace at lambda, at the point lambda, which are generic. That means that in our parameter is a lambda not equal to 0, 1, infinity. Okay. They can express using the using the hypergeometric function HP at 1 over lambda. Okay. So the contribution from lambda corresponding to elliptic points, they can be expressed as Jacobi sums. And for lambda corresponding to a cusp, we contribute 1. Okay. Then for the first 2 groups, which do not have the minus identity, so it's a gamma 1, 4 and the gamma 1, 3, we have the level. Okay. Now for the forms with an even weight, and the results are very similar to what we just described. For the odd weight, we'll find out that Heca trace is equal to 0, and the primes count to -1 modulo the level. And for the primes count to +1 modulo level, we have similar contributions at the points which are generic and elliptic. Okay. We have to be careful about contribution corresponding to the cusps. Okay. Because in this case, we have 2 kinds of cusps. We have regular cusp and irregular cusp. At the regular cusp, contribution is 1. At irregular cusp, contribution is -1. And gamma 1, 4 has 3 cusps, and 1 of them is irregular. 2 of them are regular. Okay. So let me give you an example. Okay. So the 2, 4, 6. Okay. So this comes from the quaternion group. And the first weight that for which this group has a non-trivial modular form is the weight 8. Okay. In that case, it's 1-dimensional. It's a square of the weight 4 form for the OB1 group. Okay. So in this case, the Frobenius trace, the Heca trace is the same as the Heca eigenvalue for the form. Okay. And that is expressed in terms of the quantity we call that A lambda P, and A lambda P is expressed exactly using the hypergeometric character sum. Okay. And for the APH for square itself, well, it's because it has a weight 8, it comes from the symmetric powers. So there's some polynomial relations to express that. And that the remaining part gives you contribution for at the 3 elliptic points. Okay. Well, by the Jacobi-Lehner's correspondence, this form for the 2, 4, 6 corresponding to the weight 8 form for level 6. So this is also gives you the AP for that weight 8 form. Okay. So I will end by talking about some applications of our explicit trace formula. So first, when we stated the theorem, we give the trace of TP on the whole space, but actually we can give the eigenvalue of TP on the space by computing the powers of Frobenius. Okay. And the second is that although we only gave a uniform treatment for the 7 groups, but if we have a subgroup, gamma prime of our group, and if we have an explicit curving map over Q, then we can pull the sheaf back into from the X gamma to X gamma prime, and we get explicit Heca traces for the subgroups. Okay. And the third one is that from, say, explicit values for this particular example, we when we choose a prime, say choose prime t equal to 7, from that gives us explicit expression of the 3f2 function at a very special point, and you see its explicit value. So this is due to the work of Yifan Yang. And the last one is that if we look at the Ramanujan delta function, so the weight 12 curve form for SO2Z, or we call the tau function. And we find out, we look at tau at prime p, we look at its value modulo 10, you will see that it's non-zero modulo 10, except for the one class when the prime p's come to 9 modulo 10. And we know that here there's a famous Layman's conjecture, which says that all the tau n should be non-zero. But here we first look at what happens to tau p. Just by modulo 10, we get a bunch of fairly good information. So thank you very much for your attention.
Is there any questions? Any questions from the audience? Bill?
Well, I just want to add a comment that you mentioned SL2Z was done by Zillier. In fact, SL2Z was done by Ihara, except that Ihara didn't calculate in terms of hypergeometric functions. I just want to throw in Ihara's name because it's a very famous paper was in 1967. That's the only comment.
So you mean the history part? I should add, yeah.
It's more. Anyway, I just want to mention Ihara because he was a real pioneer in these kinds of calculations. That's all.
Any more comments? Okay, let's send Winnie again for the wonderful talk.
Thank you.